Hi everyone, welcome back to Mind Maths with Amina. In this lesson, I'll be solving the practice questions given in the Statistics 1 study guide provided by University of London for their EMFSS degrees. The first question is, they want us to calculate the probability that when two fair dice are rolled, the sum of the upturned faces will be an odd number, less than 9, exactly 12, exactly 4. Okay, for such questions, it's always nice actually to make this table where we consider all possible scenarios. So you could either see the first die showing us a 1 or a 2 or a 3 or a 4 or a 5 or a 6, and the second dice could also either get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. So these are all possibilities for what you can see on the die, both the dice. So if one dice shows a 1 and the other one also shows a 1, then the sum is going to be a 2, right? So when the first dice shows a 1 and the second shows a 1, the sum is going to be a 2. Okay, let's just call this the first die and this the second die. Okay, so the first die shows a 1, the second shows a 2, the sum is going to be a 3. A 1, 3 is a 4, 1, 4 is a 5, 6, 7, you get the picture. There's going to be 3, 4, 5, 6, 7, 8. The first die shows a 3, the second shows a 1. We add them, get a 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. It kind of gives you a nice pattern where entries on the diagonal are actually this is the diagonal of a matrix. Anyhow, but you can see like these entries are the same, sort of like a symmetric matrix. Anyhow, let's see what is the probability of an odd number. So odd numbers are 3, 5, 7, right? So let's see that 3, 5, 7, 3, 5, 7, 5, 7, 9, 5, 7, 9, and again 7, 9, 11, 7, 9, 11. So we have a total of 36 possibilities, right? And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Or basically you could just multiply 6 by 3 to get an 18. So this is a 1 by 2. So there's a 50% chance of getting an odd number. Okay, what about getting a number? Let's define x as the sum of both dice. So what is the probability that the sum is less than 9? We can equally write this as 1 minus the sum being actually greater than equals to a 9. So because that's going to be easier to see. So the sum being greater than equals to a 9, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 possible favorable outcomes, and the total number of outcomes is 36. So we have 26 over a 36. Okay. What about the sum being, the probability of the sum being exactly 12? There is only one possibility of that happening. So that was easy, 1 over 36. Okay, the probability of the sum being exactly 4. We can see there are only 3 possible favorable outcomes. So the number of favorable outcomes is a 3, and the number of total outcomes is a 36. So 3 ones are 3, 3 twos are 6, so 1 by 12. Okay, the first question is done. The second question. A simple gambling game is played as follows. The gambler throws three fair coins together with one fair die and wins £1 if the number of heads obtained in the throw of the coin is greater than or equal to the score on the die. Wow, this is confusing. Okay, let's okay, he has he throws three fair coins. Okay, let's just draw three fair coins. Three fair coins. Okay, and then he also throws a dice. Okay, this is the dice. Coins have two options, right? Either head or a tail. Either head or a tail. Either head or a tail. And with a die, the possible options are 1, 2, 3, 4, 5, 6. So there are two possible outcomes here, two possible outcomes here, two possible outcomes here, and 6 possible outcomes here. Okay. He's going to win £1 if the number of heads thrown is greater than or equals to the score on the die. Okay. So that means that he can only win when the score on the die is actually less than 3. Why I say this is, suppose the die showed 6. It's not possible for you to end up with 6 heads because there are actually 3 coins. So this is not, he can't win here. And if the die shows a 5, again he can't win. If the die shows a 4, he can't win. But if a die shows a 3, then there is a chance that he gets all 3 heads together, and therefore he wins. So let's find this. So suppose that our die showed 3. Then he can only win if all 3 coins give us heads. So we have one case where this is possible. Okay, suppose the die showed a 2, right? So if he had 3 heads, he would have won because the number of heads is greater than, right, 2. And suppose he had actually 2 heads. So what are he could have gotten a head, tail, or a head, tail, head, or a tail, head. So these are 3 scenarios where he would have gotten 2 heads, right? And this is one scenario where he would have gotten 3 heads. In all these cases, he would have won. So there are 4 cases, such cases where he would win. Okay, what happens if the die showed a 1? Then he will win if there are either if there are either 3 heads, because 3 is greater than a 1, or there are 2 heads, right? So this is another scenario where he can win. So these are 3 events here. There's a one possible scenario here, and he'll also win if there is just 1 head, because he said greater than or equals to. So we could get a 1 head as follows: H, T, 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 H, T, or T, T, H. So these are 3 scenarios where we could get 1 head. So the total scenarios in which he's going to win is 7 cases. Okay, so therefore our favorable outcomes are a 1 plus a 4 plus a 7, which is equals to a 12. What about our total outcomes? So the total outcomes are actually the first coin can give us either a head or a tail. So there are two options there. There are two possibilities for the second coin, two possibilities for the third coin, and 6 possibilities for the last, which was a dice. So there are a total of 8 into a 6, 48 outcomes. Okay, so therefore the probability that he wins is the number of favorable outcomes, which is 12, divided by total number of outcomes, which was a 48. So the probability of winning is a good 25%. Okay, the last question that I will cover in this lesson is question number 3. It says that 3 fair dice are thrown and you are told that at least one of the upturned faces shows a 4. So this event has already occurred. Using this fact, determine the conditional probabilities of exactly 1 4, exactly 2 4s. Okay, so we can actually define a variable x as being the total number of 4s on the upturned faces. Okay, so for instance, before we start the question, if I say the total number of 4s is actually a 0, no 4s, so this means that we could get a 1, 2, 3, 5 and 6 the first time, and then the second dice should also show this, and the third dice should also show this. So that means that these are 5 possible outcomes here, 5 possible outcomes here, 5 possible outcomes here, right? So this means that if I want to say that the number of upturned faces, there's 0, none of them is a 4, then there's a 5 by 6 chance that the first die does not show a 4, and there's a 5 by 6 chance that the second dice doesn't show a 4, and there's a 5 by 6 chance that the third dice doesn't show a 4. So we have a 125 over a 216. Suppose I say that there is the total number of 4s is a 1. So it could be that the first dice shows us 4, but the remaining 2, the other 2, don't show me this. Okay, or there's another possibility that the first die actually does not show me a head, but the second one does show me a head, and the third one, I meant 4, does not show me a 4. Or it could be that the first dice doesn't show me a 4, and the second dice does not show me a 4, but the last die does show me a 4. So the number of outcome fixed here, the last die can only show me a 4. So their number of outcomes is 1. This can show me either a 1 or a 2 or a 3 or a 5 or a 6. So therefore the second dice, we have 5 possible outcomes, and the same applies here. So basically what we can see is we have a 3 being multiplied by 5 5s are 25 and 216. Okay, so we have a 75 over a 91. Okay, what if I say the number of upturned faces, total number of 4s on the upturned faces is a two of them show 4. Okay, so let's see. The first one shows me a 4 and the second one shows me a 4, but the third one does not show me a 4. Okay, this is one possible scenario. Then the first shows me a 4 and the second one does not show me a 4, but the last one does show me a 4. Okay, what else? The first one does not show me a 4, but the second one does show me and the third one does show me. In all these possibilities, we have 2 dices that are showing me a 4. So the answer is a 3 multiplied by a 5 over a 2, 1, 6, right? So we have a 15 over a 2, 1, 6. Okay, what if all 3 dice showed me a 4, right? So the probability of that happening is the first one showing me a 4, the second one showing me a 4, and the third one showing me a 4. So the possible scenarios here is, let me think about this one. We are going to get just 1 out of a 216. Yeah, I think that makes sense. Okay. So we were just doing this as an exercise. Okay. What we are actually interested in, that they've told us that at least one of the upturned faces shows a 4. So what they've actually told us that the probability, we need to find the probability of at least one upturned face being a 4. So at least one upturned face being a 4. So there are actually 2 ways of doing this. They're asking for the probability of the number of 4s that you see exceeding 1. So one way we can do this is we can say, okay, this is possible when you see 1 head, or you see 2 heads, or you see 3 heads, right? So this is one way you can do this, and we had already calculated these. We have the first one was a 215, 125 plus a 75 plus a 15 over 216. Oh, sorry. Oh, the 0 is not included. 1. We had to start with 1. So 1 is a 75. Okay, a 75 plus a 15 plus a 1 over 216 over a 216 over a 216. However, this way is kind of like a bit incompetent, because we know that since probabilities have to add up to a 1, so the probability of the number of upturned faces, 4 being 4 exceeds 1, is just 1 minus the probability of the number of upturned faces that are 4 would be strictly less than 1, and that's the probability of you seeing no 4s, right? And that happens, we've also already calculated that that's a 125 over a 216. So therefore we need to calculate a 216 over 125 over 216, and therefore that is a 91 over 216. So I would this method is generally preferred and therefore recommended. Okay, let's start by answering the first question. It's asked us to find the probability of exactly 1 4, given that we had at least one 4. Okay, so the probability of the upturned face showing us 1, 4, given that the number of 4s seen was at least 1. Okay, so this is the probability of x being 1 intersection x being greater than equals to 1 over the probability of x being greater than equals to a 1. So the only point of intersection is x is equals to a 1, and the denominator is x is greater than equals to 1. We already have calculated this. This is a 75 over 216, and this was a 91 over 216. So therefore the possibility is 75 over a 91. Part B asks us exactly 2 4s. Okay, so the number of 4s is exactly 2 given that x is greater than equals to a 1. So this means we need to see the intersection between these two events. Then the only point of intersection is exactly at 2, right? So we have already calculated the probability of x is equals to 2, which is 15 actually. 15 divided by 216, and this was a 91 divided by 216. So we have a 15 divided by a 91. I would like to say that when you're doing like probability questions, right now for instance I'm looking, I could also use the counting principle to solve such a question. For instance, what I can there's another way that I could think by using the counting principle, which is that I count the number of possibilities. For instance, if I'm just interested in the probability of there being at least one of upturned face that shows 4, so I can actually think of the first being restricted to a 1, 4, and then the other ones can be anything. Similarly, the third dice showing anything. So this is the first, there's just one option here. There's 6 possibilities here, 6 possibilities here. So a 1 and 6 and a 6 gives me 36. Okay. Then we could have the first die actually not showing us a 4. So that would be a 1, 2, 3, 5, 6. But the second one does show a 4. And then the last one does can show us anything. So anything. So that means there are 5 possibilities here, 1 possibility here, and 6 possibilities here, so 30 over here. And the last, okay, there's not a 4, this was not 4, right? So this is not a 4, so it could be 1, 2, 3, 5, or 6. And then again, it's not a 4. So either 1, 2, 3, 5, 6. But remember, it had to be greater than equals to a 1. So this has to be a 4, then you don't have an option here. So over here, we had only 1, 4. And over in this scenario, we could have either 1 or you could have 2. And in this one, you could have anything like either 1, 4 or 2, 4 or 3 4s. These are the scenarios. So there are 5 options here, 5 options here, 5 options here, and only 1 option here. So you have 25 possible scenarios here. So what are the total possibilities? We have a 36 plus a 30 plus a 25. So we have 91 favorable outcomes. So similarly, like we can solve the remaining question using the counting principle again. So for instance, if they say, okay, what is the probability of getting 1/4 given that you had at least let's just not write it in English. The probability of 1/4 given that at least there was 1/4. So in this scenario, what I can again visualize these boxes, right? And I want to create a scenario where I imagine there being just exactly 4. So what is if this is stuck at a 4, then this cannot be a 4 and this cannot be a 4, right? So there are one possibility here and 5 possibilities here, 5 possibilities here. And then we have an option of this not being a 4 and then this being stuck at a 4. So there's a 5 options here, 1 option here, and the last not being a 4. So another scenario in which we have five possibilities here. And the last scenario is that you get not 4 on the first, not 4 on the second, but you do get a 4 on the last. So 5 into 5 into a 1. So we can imagine the boxes and imply and use the counting principle again, right? So writing this down, the first shows me a head, the second doesn't show me a head, the third doesn't show me a head. Plus the first doesn't show me a head, the second shows me a head, and the second last doesn't show me a head. Plus the first not showing a head, second not showing a head, and the last one showing a head. And what were the total possibilities? 91. We've already calculated that, right? So this gives us a 3 into a 25 over a 91, which is a 75. We can use the counting principle again when it asks for at least 2 being dice showing a 4, provided that there are more than 1. Again, I can make this visualization of there being 3 coins, and this has to be a 4 and this has to be a 4, but this need not be a 4. The second scenario is that this is a 4, this is a 4, but this is not a 4. Or it could be the first one is not a 4, this is a 4, this is a 4. So we have just one option here, but there are 5 options here. And then we're just stuck with one option here, 5 options here, and one option here. 5 options, one option, one option. So we have a 1 into 1 into 5 plus a 1 into 5 into 1 plus a 5 into 1 into 1 over total possibilities, which was a 91. So again, you can make this visualization in your head and count the possible outcomes using the counting principle. And then again, we have a 15 divided by 91. Okay, I understand if you feel overwhelmed, but because probability is actually a difficult topic, but with practice you'll get it right. So don't feel overwhelmed and just practice away and you'll get it eventually. Take care for now.